Okay, in this video, we take a look at what will happen when we inscribe a sphere inside a tetrahedron and then circumscribe the sphere, which means taking it through the four vertices. Starting with the inscribed sphere, what ends up happening is we realize that because it's a regular tetrahedron, all of the important lines are going to be the same. And so I've drawn in from vertice up here to the center of the base, and then vertice on the left, the center of that side, and I could do it again here as well, vertice there, to center of that side. And what you recognize is this point right here is going to be both the center of the inscribed circle. The inscribed circle is going to be tangent to the faces at the endpoints there, and the circumscribed circle, because if this is the center, then this length here is going to be the same in all these places. And so that gives us a really important insight into how to do the problem, because the height of the tetrahedron is made up of a radius of the inscribed circle sphere and a radius of the circumscribed sphere. So to calculate these, we take the fact that the height of a regular tetrahedron can be found by side root 6 over 3. And if you're unconvinced by that, by telling you, I have a video done that shows you how to find the height of a regular tetrahedron given side length. What we want, when we found that, we looked at this triangle right here. We looked at the triangle of the radius of the face, the distance from the center here to one of the vertices, and then the center of these spheres to one of the faces. Now, let's call this R, little r, and so our triangle is going to look like this, where this is R. This is the radius of the equilateral triangle, which if we draw in and you get a 30-degree angle here, if this is S over 2, you divide by root 3 to get S over 2 root 3, which turns out to be S root 3 over 6. Multiply by 2, and we find out that that radius is S root 3 over 3. And so this length is S root 3 over 3. And then, if this is R, this length is going to be the same as that length, and so it's going to be the height minus R, because this whole thing is the height, this length is the height minus R, so this length is also the height minus R, and our height is S root 6 over 3 minus R. It's a right triangle. What we're going to do is apply the Pythagorean theorem. Side root 3 over 3 squared plus R squared equals side root 6 over 3 minus R squared. All my things that might look like a 5 in this problem are S's, just in case you're wondering. Square both sides, do all your squaring. Well, this is going to give you 3 over 9. So side squared over 3 plus R squared equals, when you square this, you get side squared, 6 sides squared over 9, which is 2 sides squared over 3, minus 2 times the product, so SR root 6 over 3, plus R squared. All right, a nice thing happens right off the bat. R squared cancels. If I subtract S squared here over 3, I get S squared over 3. And then if I add this to both sides, I can over here have 2RS root 6 over 3. Multiplying both sides by 3 cancels out to 3. The S has a value, so I can divide both sides by that. And that leaves me with 2R root 6 equals S. We want to find a formula for the radius, so we need to divide both sides by 2 root 6. So then we rationalize root 6 over root 6 gives us 6s root 6 over 12. So the little r equals s root 6 over 12. But then if you remember, we found out that the height is the other side of the height is the radius of the circumscribed sphere, and that's just going to be the height minus the small radius. This is your height. It's the same as, and so we'll call our big R, it's going to be the height minus little r. And so 4s root 6 over 12 to make the denominators the same. That means that big R equals 3 root 6 over 12, which times side length, forgot that. And that gives you the same as side root 6 over 4. And so the radius of the circumscribed sphere is side root 6 over 4. The radius of the inscribed sphere is side root 6 over 12.